Hello there. Welcome to an interesting problem. It's called the twin paradox. Many of you have probably heard it. Let's go over the actual statement of the paradox and then learn how to actually resolve the paradox. It's just a paradox because on the surface there's a contradiction, but actually there is no contradiction. Okay. So consider there are two twins. Let's call it A and B. So maybe they are on Earth and they are A stays home and B travels to a faraway place at high speed or whatever, any speed, and then turns around and comes back. So this drawing is from what A is looking at, B is going and B is returning, right? So that's why it's perspective of A. So perspective of A is like that. So when it returns, based on time dilation, so this is the time dilation. So when B is traveling, a clock that goes with B is at rest. So if you map it onto this, you will see that if B was, so this is B is traveling, and then this is A is at rest. But the clock is in B. The B's clock is actually moving with respect to A. So the A will give time according to this. So if we go from here to the destination, then this is the gamma for the speed v. So gamma is 1 over square root of 1 minus v over c square, right? And this is greater than or equal to 1, and so time elapsed in 1 will be larger than time elapsed in 2. And so I'm going to use a notation that makes it clear which time and which frame we're looking at. So this is the time that B will see in its frame, and this is the time that A will see in its frame. So this says for the round trip. So this is for the round trip, and this for the round trip. You expect A to have seen longer time elapse and B to have seen shorter time elapse. Just based on this, it goes from here to there and comes back just from this part of the trip. And this, because of V can be positive or negative, so B is positive this way and then V becomes negative when it's coming down, the square actually doesn't affect it. So from this perspective, A would age more than B when they come back. And that makes no perfect sense from the relativity. We'll see what the problem is, okay? Now when you look at the B's perspective, the same thing. So B is sitting, but A is going on this side with same speed of that there, and then A is returning. So if you're sitting in the, say, B's spaceship, you're going to see this scenario. So now we use the same logic as above, and so B and A role appears to have reversed, and so you would think, shouldn't that be the case? And this is completely opposite. So you will get an opposite conclusion based on which of the perspectives you use. And this actually is a way to confuse people, okay? And it seems like it's very successful in confusing a lot of people. So this is round trip. So only one of these can be correct, and which one? Now it turns out that this is correct, and we'll work it out. So what happens here is this appears superficially symmetric, but it is not symmetric situation. So over here, if we're thinking B is going, then there is an acceleration part here. B has to accelerate to some speed v. Used to be v equal to 0 here for B, and VB is not 0 anymore, and at constant velocity it's going all the way here, and then it has to turn around. The velocity is pointing that way and the velocity is pointing. So this part is acceleration of B is not 0, acceleration of B is not 0. So while acceleration of A is 0 in the entire, the entire trip. So this has a couple observation. A, B is not 0 during the trip, and AA equal to 0 during the trip. Now when you look at this from the perspective of B, well, A goes, there will have to be, A has to accelerate to some speed v, same speed as that, and then is to decelerate in order to come back to the original situation comparing their clocks. And then over here the A has to turn around. So that part I didn't write. So A has to turn around. So A was going this way, then it has to go this way. So there is an acceleration of A is not 0. So in this scenario is not the same as that scenario, and AA is not 0, AB is 0 during. So this is not the same. This scenario is not the same as that. So whatever you get here, to make that scenario come out the same, you'll have to make sure that B accelerates. So one way to do it is B accelerates is not compare with that, but compare with B's. This is not the correct perspective of B. Okay. So B perspective will be, okay, from the first leg, on the leg 1, let A go, and let's ignore this initial acceleration. We just ignore the acceleration, maybe for the sake of the argument. Okay, so A is going to go there. So this looks okay. This is first leg is completely symmetric, okay, because we're ignoring the initial acceleration. So A went this way, is over here, but A will keep going because I want A to have the same V constant. So the A is constant V. Acceleration of A is equal to 0. So I want to maintain acceleration of A throughout. And B was constant. It stayed here. So when at the C, at some point in the middle, okay, then at that point B has to go with higher speed to catch up. VB has to be greater than VA, and then basically VB was 0 for this time, but then he has to catch up. So there will be acceleration when this A is here and B was here. At that point B has to accelerate. So now we have a acceleration of B is not 0. So this would be the scenario when they catch up. In the perspective of B is still accelerates, right? Because when a frame is accelerating, it can detect its acceleration. So B is accelerating, A will never accelerate, and they will meet up. So the B will stay with a 0 velocity for some time when A has moved to the left, and A continues on the leftward journey. So these two, so over here, delta TA you're gonna find, and delta TB you're gonna find for the entire, for the trip, and you will find exactly same values when you delta TA for trip and delta TB for trip. So this will be same as that, and this will be same as that. So I'm going to work out this calculation, and you will see that these two, this is the correct perspective of B. And in this correct perspective, compared with the correct perspective of the original perspective of A, there is no contradiction. All these values for the trip are exactly the same. And so even in this perspective, you're going to see the delta TA in A is greater than delta TB in B, just like over there. And I'm going to work this out with a simple example. Okay, so I hope you understood that there's no contradiction, and we still are going to, it's just the perspective that people confuse with. They say that this is the perspective, but this is not the perspective. This is not correct perspective for B, because in this perspective you ignore the fact that the B has to accelerate and A doesn't accelerate. In any scenario you think of it, all perspectives that are going to have B together, and then later B becoming together, B and A and B become together again, you cannot have A accelerate, B has to accelerate. Okay, they'll all be equivalent. All right, so let me give you a numerical example. Okay, numerically set this up. Okay, let's work out the two perspectives. One from the perspective of A. A is the one who is not accelerating. Another perspective will be perspective of B. Okay, so in A perspective, think about what's going to happen. B would have been at rest. And then B start to accelerate. Let's write down here. B is equal to 0. Okay, so V, I'm just writing V of B with respect to A. So these are all with respect to A. And it travels for, at this time, we'll say T at A is concerned. At this point, T with respect to A, it has traveled for 10 years. Okay. And then it decelerates to 0 and then accelerates in the opposite direction. So there is the, from here to here is the acceleration phase. Of course, here to here was acceleration. I should erase this. This is over here. Yeah, so that's not acceleration. The acceleration is between this end of this to the beginning of this. So let's you know what I mean in this, right? So you don't need to pay attention to some of this. So, and from here to here is, so this phase, this is where the time dilation will take place. This is where the special relativity applies. Okay, and especially equations will apply because you have a inertial frame, another inertial frame. But here B is not an inertial frame. So here B is not inertial frame. So I don't have these equations. There's a special way we can say B is infinitesimally we can look at it. B is in one inertial frame, and a little bit later it's another inertial frame, a little bit later it's another inertial frame, and so we can accelerate it with using infinite number of inertial frames. But we're not going to do it. We can just assume that between here and here, we can assume that delta t is 0. We're going to just assume that. Over here, the same thing, we're going to say B is non-inertial. So we don't have a special relativity equation we can deal with it. So delta t will, for this thing to happen, we can just assume that it's 0. And then we have this is again is both inertial frames. So this is special relativity equations will apply. And then over here, B is non-inertial. And so again, I'm going to say it's slowed down in almost no time. Okay. All right. That would mean high acceleration, things like that, but I'm not going to address that. There are kind of tricks you can play and try to calculate that time. Non-accelerating frames. Sometimes people say, okay, how do we can use a special, we can use a principle of equivalence of Einstein and try to map it on the gravity problem and then use the gravity formulas to use it. I'm not going to do that, okay? So that's just something that might be in the future when I do address some special general relativity, but it's not on the docs for me for some time, okay? All right, so this is the phase, and this is the phase we will add up. Okay, so delta TA is 10 years here, so we just say between these two times from here to there, so T at A now, when B returns, is 20 years. So it went on 10 years and went back 10 years approximately. So the T, so if this one for 10 years, you can just say what is the T? The question is what is this time in the frame B? So we want to know the time here in frame B. Well, so this will be like a clock I put in B and it's moving with respect to A, right? So T of B will be 1 over gamma T that was in A. And this is time dilation, 2 time systems, right? So basically this formula is when they started, this is the frame A. In the frame A, T was 0. And frame B, T was 0. So now we have 2 clock system, this clock and this is the final clock. In this situation, so in this situation, clock compared with that both are 0, and over here we have a B now. B has gone, B is showing some time, and A will be now, because B has been traveling, A will be showing some other time. So because B has been moving with respect to A, the B will have less time and 1 over gamma like this. So what's the gamma here? So gamma is 1 over square root of 1 minus, and we're going 0.5 C, so this will be half square, and that will just turn out to be 2 over square root of 3. 4 minus 1 is 3. So 1 over gamma is going to be square root of 3 over 2 and times 10. So this is equal to 5 square root of 3 years. And then over here the calculation will be same because the square is the same. A square gives you negative becomes positive, and then so this will be the same. so delta t on the B clock for this step will be exactly same as that, 5 square root of 3 years. So delta t in A, this is total. So so starting from event, let's call it event 1, they compared now, and let's call this event 2, compared now. So if you add up all the times, now this is 0, we're taking this is 0, this is 0, we're adding all, consider them to be 0, then I just have these two, so this is equal to 10 years total. 0 plus 10 years, there's some other things, and delta t total in the B will be this plus this, so 10 plus 10 is 20 years, and this is 10 square root of 3 years. So that, and this definitely is of course less than 20 years. So that's so they will age this amount. Now let me write this down and see, when I do from the B's perspective, I should get exactly same answer, okay? And that's what a lot of people don't understand. You get exactly same answer. It doesn't matter which perspective, as long as you have B accelerating and A not accelerating, okay, throughout the journey. So let me or if this A's acceleration is happening, is only in the phase I'm going to ignore. All right. So here is a T in the A frame is 20 years, and T in the B frame is 10 square root of 3 years. So I'm going to just save that and erase everything. Okay, so this is the perspective of B. Okay, from which accelerates, right? Okay, so we're supposed to get the same answer in both A and B, and we have to carefully lay it out so that it's works out. So first thing to notice is that we need to keep track of the speeds both A and B. So we need a third frame, okay? So there will be a third frame which is at rest. Here both A and B kind of move, and the question is move with respect to which frame. So we will say we have a third frame, I'm just gonna call third frame, in which they are at rest. So these are all with respect to the third frame. So of A with third frame. And this is a B with respect to third frame. And this is the V of A with respect to the third frame. And this is a V of A with respect to the third frame. And this is with respect to the third frame. This is with respect to the third frame. All of this, okay? So V of A with respect to the third frame. And this is with respect to the third frame, okay? Now we kind of agreed that we're going to ignore this times for this, okay? In the earlier part we ignored it, and same steps. So whatever happened in this actually happened in here. So we can just say these things happen delta t0 in all frame, okay? So this is a very short period of time, and we're just looking at time. Okay, so thing to do is we want this time with respect to the third frame, which is the same as in the, so right now this is 0 and this is 0. So the time in with respect to B, so the time for this, time in the third frame will be same as time in B. So they will be all the same here. because B is at rest and A is moving, right? So what is the T3 will going to be? T3, and this should be equal to more than what's in A, right? Now this step, the first step, had lasted for 10 years. So this will be like a 5 is square root of 3 years, and so this will of course correspond to so this should be based on this relativity. So relativity will say that check, it should be 10 years, right? Because the first step was 10 years. So in A, so so you have a relationship here will be T3 is so the clock is, you can see the T3 clock is let's write down the T3 like this. So T3 is staying here more or less, okay? T3 is staying here, so the clock is here. In this clock, the time is that when A is over here, so this clock has a corresponding clock here. So this is T3 in here. So this T3 from the perspective of A would be actually a smaller time. So it's going to be 1 over gamma what T will look like. So for the T in A will have this relationship, right? So let's see, and the gamma is 2 over square root of 3 as before, because they speed the same. So when we flip this over, so let's say T in A for this step is going to be okay, I confused me. Bring the gamma over there, then I have a 2 over square root of 3 times T3, which is 5 square root of 3. So this 10 years. So this step in A will be 10 years as before, okay? How about this step? This step is here. I need to figure out what the speed of the V has to be. So the V has to go from the original place to a longer distance, some distance. This distance is the distance of the entire trip, right? It has to cover in some amount of time, okay? And I'll say I want to draw these pictures in a space-time diagram. It turns out this is less helpful in terms of doing the calculation than a picture that I'm going to draw, which I'm going to draw a time axis this way and x-axis this way in the frame 3. I'm going to draw this whole journey in this, and then we can see these calculations a little bit clearly, okay? So so much easier to visualize in this picture. So time in the third frame and the space in the third frame. So if you look at B has actually gone, stayed at the origin, and only time is increased in third frame for B, and it's gone up to time. Time was 5 square root of 3 years. Okay, and then then what's happened is at that time, if you look at A actually at constant velocities, this is constant velocity, the straight line will be constant velocity, like dx dt will be constant, and so this A with respect to that has been, this is A and this is B in this diagram, and A will kind of continue. A will continue at constant velocity for another 5 and it's got 3 years in this, right? So it's gonna be over here. Okay, let's figure out some time t. It will be over here, and we want B to have acceleration, and B will meet over there. So here is the phase in which acceleration of B is not 0. So that's what we want. We want turnaround part to be in the B, right? Not in A. A doesn't turn around. Otherwise, you are not really looking at the same problem. So this is the meet unless time be t. At that time, t in A will be 20 years. So from there, and this thing is going at 0.5 c, we should be able to get this what t in 3 will be. So we already wrote down t in 3 is gamma of this gamma of 0.5 c times t in A. So the local clock in A is just using time dilation, and that should be equal to 2 over square root of 3 and t in actually 20 years total, you know. So this is 40 over square root of 3. Okay, so this is equals to 40 over square root of 3 years. Okay, let me pause and think. So a couple of things to notice is this is equals to, at this point, t in 3 and t in B. Now we know t in 3 here. How do I convert that in, what is the t in B here? That's what we want, right? T in B here. And we know so if we just need to convert between this 3 and then B, but that we need the speed. This speed will be the distance it traveled, so distance in 3, and the time, that delta t in 3. So this is the V of B with respect to 3. So V of B with respect to 3 will be distance that traveled 3 over delta t over which B traveled that distance. So this is all 3. So this is very simply, and this one was 0.5 c. You can see the A had traveled at 0.5 c for this amount of time. So this should be 0.5 c travel at 40 over square root of 3 years, and delta t of 3 was just this minus that. 40 over square root of 3 minus 5 square root of 3. So I think let me work this out. So you have a square root of 3 times 0.5c times 40 over square root of 3 divided by 40 minus 15. So the square root of 3 cancels out, and this is 20c divided by 40 minus 15 is 25. So 4 over 5c is 0.8c. Okay, so this is going to go at 0.8c. So for the gamma for corresponding to that, gamma for this gamma of the b with respect to 3, so everything I'm going to go to 3, right? So we already know this, so we're going to figure out the time in the b corresponding to that. So gamma of b is going to be 1 over square root of 1 minus 4 square over 5 square, and this is going to be 5 over 3. Okay, so we're just looking at this part. So the t in b will be 5 square root of 3 plus, right, 1 over gamma of 1 over gamma of this delta 3, this time over which b is moving, right? So delta 3 of b, which is 40 over square root of 3 minus 5 square root of 3. So I did add up here a little bit, and then this cancellation will take place appropriately. This is going to get me square root of 3, and this gives me 5. So 5 square root of 3 plus 5 square root of 3. So that's total time. This is our total. And this is the first phase, this part, and then for that part is this whole thing. For that part, 10 square root of 3. So here again, even in this perspective of b, as long as do it correctly, right, we get t, this is total time in a is 20 years, and time in b is 10 square root of 3 years, which is the same as that. So I hopefully this helps clarify, and there are a lot of really wrong explanations out there, or kind of crazy explanations of twin paradox out there. But I like that we worked out from both perspectives. But no matter which perspective you work, you have to be willing to say that AA never accelerates. AA is always 0, and AB, which is the space traveling so-called twin, and this is the one that accelerates. This doesn't accelerate. As long as you maintain this, and then you work out from each perspective, you can get exactly the same answer. So there's no inconsistency or no problem with twin paradox. Hope you enjoyed it. If you enjoyed it, please hit a like button. You can check out my website also. Lots of the entire book is there, and you can subscribe to this channel. Helps the channel grow. Thanks. Take care. Bye.